Today we're going to look at the activity of some metals. We're going to look at physical properties and chemical properties and try to establish some relationships as you go down the rows of the periodic table and across in a period on the periodic table. So 4 metals we're going to look at in particular are lithium, sodium, magnesium, and calcium. Before I get started, I want to point out some safety precautions that I'm taking. Of course, safety goggles, and since I'm going to be directly handling some chemicals, I've got gloves. I also have large buckets of water standing by, and as I undo the chemicals to show you the chemicals themselves, you're going to see some safety precautions that are taken just in the storage of the chemicals themselves. So let's get started. First, I'm going to look at the lithium. Notice that lithium is stored almost in a paint can, a big metal can. So I'm gonna need a screwdriver to actually even pry open the lid to get to where the bottle of chemical is stored. That bottle is stored in a separate baggie. Oh, lots of rocks going everywhere. With lots of stones and rocks around it. And then that little baggie is tied off from the air. So we're gonna have to unscrew a little bread tie, twisty tie around the bag in order to get the chemical bottle out. And then there's another layer of protection to protect it from the air, something called parafilm. So this goes around the outside, the top, in order to make the bottle itself airtight. So we're gonna have to get that parafilm off in order to be able to even open the chemical bottle. Then when I open the bottle, it is stored inside of oil. So all of these are indications that exposing this chemical to air and water is not the best idea. So we're gonna try to keep it stored like that. In order to examine it, I'm gonna pull some out, a small little piece. You see it's shiny black, and it actually can be cut with a plastic knife. We see we can dive right in there and kind of expose a shinier piece. Shiny, shiny, shiny for the lithium. Now I'm going to cut off just a small little piece to put in my petri dish and put the rest back in the oil. And then I want to seal it back up immediately in the oil. Sealed back up. I'm going to put a fresh piece of parafilm on it so that just stretches and fits to make it airtight again. Then I want to put it back in the box. Back in the can, I should say. So first into the bag. Twisty tie. And then in order to get it to fit in the can with the rocks, you have to actually pour out some rocks, stick it in there, and then pour the rocks back on top. Seal the paint can lid back up. So now our lithium is back into proper storage. So let's take a look at the physical properties of the lithium. You see a very shiny side to the part that I just cut. And then if you look at the part that was in the oil, it's a little bit darker. So that tells you it does react over time with the air. But when it's freshly cut, see how shiny it was. And then we also know it's very soft since I was able to cut that with a plastic knife. So that's lithium for you. Now on to sodium. So sodium again is stored in a big old paint can. So we need our screwdriver to open up this part of the storage. Again, stored in rocks. So I'm gonna grab my bucket and pull out the bag. Bag stored with a twisty tie. And then inside the bag, I have the reagent bottle. We have parafilm around the outside to keep it nice and airtight. So that's what we're gonna have to remove next. One way or another. There we go. And then as we open the container itself, it's again filled with oil. And then we have these small pieces of sodium that we can put here in our Petri dish to observe. So I'm just going to take out one little piece, and you can see the oil that spreads out surrounding the sodium. So again, you can see it's nice and soft, cuts with a knife, the inside of it nice and shiny, but it is much lighter in color compared to our lithium. So, and if you look back at the lithium, you can see the part that we cut that was so shiny is already getting dark. So it's when you expose it to air, it starts to react right away. So that's why we're storing them in oil so airtight. So now that I've showed you the sodium piece, I'm going to put it back away. We've got to put these things back in storage right away. So back in the bag, bread tie. Oh, nope, forgot the parafilm. Fresh piece of parafilm every time. So we're going to spread that out and make it so that it makes a nice airtight seal around the cap. Protect the sodium from the air. Then back in the bag. Then bread tie, twisty tie. And then to get it to go back into the metal can, we got to dump out some rocks so that it sits deep inside. And then pour the rocks back on top. Then we will seal up the metal can. So we've got that nice and sealed. So that is lithium versus sodium. Notice as I went down the row, it was much easier to cut the sodium with the plastic knife. So that would indicate it being much softer. Next, let's look at magnesium. We're going to go over to group 2. So magnesium is not stored in a paint can, but it does have the parafilm around the outside to protect it from the air. So we are going to have to remove that air barrier from our magnesium so we can pull it out and take a look at it. Dump some of these out. And we call these metal turnings. So the metal is shiny still. It is darker. You can see there are some like inkling cuttings, kind of, it's rough on the insides, and it does not cut so much with this plastic knife. But I can take a piece and, oops, if I apply a little force, it snaps. We would call that being brittle. Snap it in half. So our little metal turnings. They don't cut, but they do break. There's another form of magnesium you may be familiar with. We use this in our molar volume of a gas law lab. It's a metal ribbon. So it comes nice and stringy like this. We'll cut off a little piece of the ribbon. You can see similar color there. And these ribbons are a little more reactive. It kind of shows you the malleable nature that magnesium can have as well. And the ribbons we store in secure little baggies that can be airtight. Can't seem to get my gloves to cooperate. Here we go. So those are 2 forms of magnesium that we have. But notice I still can't really cut the ribbon, so it's not as soft as you're going to the left on the periodic table. And then last but not least, we have calcium. So calcium is stored in a little baggie. So it is one more security, but it's not in the paint cans like the sodium and the lithium were, but it is in an extra bag as opposed to the magnesium that just had the parafilm. But the magnesium does have parafilm as well. So we're going to take that off first. All right, let's check out our calcium. So kind of a whitish color. Again, not really cuttable, but you see it breaking into these little tiny pieces. So again, very brittle, but can't really cut it. Very different color, not so shiny. So that's our magnesium. Let me put some fresh parafilm back on these guys. so we can store them. Make your last observations on the physical properties of our lithium, sodium, magnesium, and calcium. The questions you're going to have to answer, we'll talk about comparing these and trying to establish patterns. What is it that makes something more metallic in character? One misconception I want to point out is that a lot of people think metals are hard, because you're thinking of steel alloys and things like that. First thing is, those metals are very far to the left compared to these lithium, sodium. They're very much closer to the nonmetals. So metallic character is going to be stronger in a certain corner of the periodic table, and that's what you need to figure out. So now I've got my metals stored back safely. We've looked at the physical properties of them. Now we're going to move on to the chemical properties of these metals. So the first thing I want to look at is my lithium. I'm going to kind of move the petri dishes to the side and bring in some water. So I want to look at what happens when I react the lithium with the water. So let's give it a try. We see some bubbling, some smoking, some signs of a very exothermic reaction. Notice I step back a little bit, use a very small amount of lithium, well ventilated area. We can see a pretty violent reaction between the lithium and the sodium. I've seen this reaction actually spark a fire before, just a small little flame as it goes around. You definitely see signs of an exothermic reaction. All of that bubbling and smoke steaming coming off. Okay. One other thing I want to do to kind of examine its chemical properties is add a drop of phenolphthalein. So as you remember from the titration lab, phenolphthalein will actually turn a bright pink in a base. So when I put it in the solution that we've created now, we can see if it's a basic or acidic product. So let's test. Pretty pink to me. So that indicates a basic product. So there's actually a set of chemical reactions that we're going to be going over in chapter 3, and you must know that metals with water produce metal hydroxides, and you can see that here by our very basic product. Next, let's look at the reaction between sodium and water. Notice the very small amount of sodium that I have prepared here. I'm actually going to use only half of what I've cut, and you'll see why in a minute. All right. Woo! See, it fizzes up into a nice circular ball. Tons of smoke. That reaction started a lot faster and is producing a lot more smoke. This reaction often produces a flame as well. But I'm trying to use very small amounts of reactants. Oh, I thought I saw a spark. Fizzle, fizzle, fizzle. All right, as that finishes up, I'm going to add in some phenolphthalein so we can see if this also produced a base. Look at all that pink. So very strong basic solution. So our sodium reacted with water to form a metal hydroxide, or probably sodium hydroxide. All right, let's look at magnesium next. So we're going to use the turnings, just give it a little more surface area to react. And so exciting! I don't see any signs of a chemical reaction. That's weird. But I do notice some of them float and some of them sink. So that kind of goes to the physical properties. If you think back to the lithium and sodium, both of those things floated right on the water and were running around on the top of the water as they were producing all of that exothermic gas and smoke and stuff. The magnesium, not really producing any of that, and some of them are even sinking. So that goes to speak to the density of the substance. Let's add in the phenolphthalein and see if there is a sign of a chemical reaction. And no pink. So what that tells me is that the magnesium is not reacting with the water. I'm not making the metal hydroxide. A metal with water should produce a metal hydroxide. So if I'm not getting the pink, then there must have been no reaction. So that's our magnesium's chemical properties. And then last but not least, we have our calcium. Now the calcium, I am doing this reaction outside and I have some dirt in my water. So I will be right back with some fresh water. All right, fresh water. So now we're going to take our calcium, which was the white brittle substance, and we're going to dump it in our water. And if you look closely, I do see some fizzing going on there, some bubbling. You also notice they all dropped to the bottom. So that again speaks to the density of the calcium. And then we can use the phenolphthalein to see if it is producing a calcium hydroxide. Metal plus water equals metal hydroxide. And pink, very pink. So yes, this definitely had the reaction with the metal and the hydroxide. So what I want you to think about now is what happens as you go down the group. So from lithium to sodium, comparing those two, we had lithium producing kind of a slower, weaker reaction than the sodium. Magnesium not really producing a reaction at all compared to the calcium. So what does that say about the reactivity as you go down a group? And then also as you go across the row. So for example, from sodium to magnesium as you go across a period. What does that say about the reactivity? And then back on physical properties, what does that say about the metal nature of a substance? Where is that the highest? So those are the questions for your worksheet. If you have any questions, make sure that you email me, send me a message. I hope this helps.
Cool.